Welcome back, Physical Science 20. This is the second part for PW1.1. So we talked about quite a few vocabulary terms, and as I mentioned, this first part has a lot of vocabulary terms. So we left off period and frequency. Although wave speed and amplitude can describe both pulses and periodic waves, period, which is symbolized, where it uses a big T as a variable, and frequency, which is a little f, whereas you'll move on in physics, it's the Greek symbol mu, apply only to periodic waves. The periodic of a simple harmonic oscillator, such as a pendulum swinging back and forth, is the time it takes for the motion to complete one cycle. Such an oscillator is usually the source or cause of periodic waves. The period of a wave is equal to the period of the source. That's a key thing to note. The period of a wave, how many seconds per cycle, is determined by the thing making that movement. So if you're swinging a pendulum, the period of your hand is what the period of the pendulum will be. In the figure below, the period t equals 0.04 seconds, which is the time it takes to make one complete cycle. If you look down at the bottom here, here's the key. And again, you'll get a formula sheet here that has all of that on it. So the period of a wave, or symbolized big T, is equal to the number of seconds over the total number of cycles. So one cycle is one complete movement of a wave. So like from here to here would be one complete cycle, one complete wavelength. Now, of course, this is going to be seconds per cycle, or sometimes that's just simply stated as second. So the same time, so over here, if you look at our diagram here, it's illustrating that as well. I can also take and look at the frequency of a wave, which is the reciprocal of that. How many complete cycles or oscillations there are per second. So if you take a look at that, it's just simply the reciprocal of period. Instead of seconds per cycle, it's cycles per second. So we'll highlight that. Cycles per second. Sometimes that's given a shortened unit of measure, and that is the hertz. So frequency is measured in hertz. 1 hertz is 1 cycle per 1 second. That's how we would get that. And then the relationship between period and frequency, we have that. If I know period, I can figure out frequency by 1 divided by t, or 1 divided by f. So they're kind of reciprocal relationships there. So those are all examples of waves in one direction. Let's look at what is considered to be waves in 2 dimensions, such as a water wave or a water ripple. When you throw a small stone into a calm pool of water, you see circular crests and troughs. So maximum areas and lower areas. So maximum, lower, maximum. We could draw circles out from that initial part from where we dip it or where a stone hits. If you dip your finger into water with a constant frequency, so over and over again like that, it would make concentric circles. Circles moving outwards from a central point as illustrated here. These kind of arrow rays here represent the movement of those ripples if we were to continue dip your finger in the water. So concentric circles are called wavefronts, centered on your finger. A wavefront is a line that represents the crest of a wave that's moving outwards. The figure A shows circles and water waves. Figure B shows the same of those water waves. Wavefronts drawn to scale show the wavelengths of the waves, but not their amplitude. So if you look at this, for example, this is called a ripple tank, and we have all these lines here could represent wave crests. And you can see if this piece of wood is dipping in and out of that water, they would move out in that direction. So we could see the wavelength by measuring. If we had a light down here, we'd be able to see that pattern on the floor. Crest, crest, crest. I could measure the distance between those crests and get the wavelengths, but of course I wouldn't be able to figure out how high these waves are. Only the distance between crests, and of course the distance between crests is a way of determining the wavelength. So that's what I could use to figure out wavelength or to measure it. Wavefronts can be straight when generated by such a device as a ripple tank, seen over here. Whatever their shape, two-dimensional waves always travel in a direction that is perpendicular to the wavefronts, and then the direction can be represented by a ray, which is a line drawn at right angles to the wave. So if you look over here, I drew a wave ray. So I have my pencil here is representing the waves that are actually made, and this pencil is representing the direction of motion. Just like here, here's a wave crest, and my ray is drawn perpendicular to show the movement in which is happening. When all you want to show is the direction in which the wave is traveling, it's convenient to draw rays instead of the wave fronts, the crests that we saw. Okay, so that's kind of an idea of what water waves look like. Sound waves, if you put your fingers against your throat as you hum or speak, you can feel vibrations there. Have you ever put your hand on a loudspeaker of a boombox? The figure above shows a vibrating bell that can also represent your vocal cords, loudspeaker, or any other sound device. As it moves back and forth, the edge of the bell strikes the particles of the air. When the edge moves forward, the air moves this way. When the bell moves backwards, we could have air moving that way. So these light and dark regions here can represent compressions and rarefactions, or you can kind of relate it to transverse waves, crests and troughs. Transverse waves made up of highs and lows, crests and troughs. Longitudinal waves, compressions and expansions. So as it moves back and forth, so when the edge moves forward, air particles are driving forward. That is, the air particles bounce off the bell with greater velocity. When the edge moves backwards, the air particles bounce off the bell with the lower velocity. So movement. So the signal that's sent in the air matches the vibration of the bell itself. The result of these velocity changes is that the forward motion of the bell produces a region where we have air pressure slightly higher than average. The backward movement produces slightly below average pressure. Collisions among air particles cause the pressure variations to move away from the bell in all directions. If you were to focus at one spot, you would see the value of air pressure rise and fall, not unlike the behavior of a pendulum. In this way, the pressure variations are transmitted through matter. So, in the case of sound, that matter is air. So sound matter is air. And of course that air entering your ear hits your eardrum and causes your eardrum to move in the same way as the bell. And then from there it goes through a variety of different things and gets transmitted into a signal. So if you're out in space, well, science fiction movies would be a little bit more boring. If you had an explosion in Star Wars, for example, you wouldn't be able to hear it because there wouldn't be air from a planet or from a spaceship seen to you, and you wouldn't be able to experience that. So they kind of lie a little bit in some science fiction movies that sounds they make an explosion, but unfortunately you wouldn't be able to hear them because of the lack of air. So you need to have air in order to comprehend what sound is. So describing sound, a pressure variation that is transmitted through matter is called a sound wave. So a pressure variation. And of course, that matter could be air, could be other things too. If you put the old idea that you could tell when a train is coming, but by putting your ear down to the railroad track, you could hear. Or of course, you hear underneath water in a swimming pool, you can hear people talking or moving, because in that case, the medium is water or liquid. Sound waves move through air because a vibrating source produces regular variations or oscillations in air pressure. The air particles collide, transmitting the pressure variations away from the source of the sound. The pressure of the air oscillates about the mean air pressure, as shown in that figure to the right. So right here, we could see that part over here. I think this is what I originally meant for to be to the right. The frequency of the waves is the number of oscillations per second. The wavelength is the distance between high and low pressure, so compressions and rarefactions. Because the motion of particles in air is parallel to the direction of waves' motion, sound is a longitudinal wave. So compressions and expansions. Okay. So yeah, that's how sound works. And sound, you can consider that to be a kind of a three-dimensional wave because it goes out in all directions and it's longitudinal. All right, I think that is it. So you should be able to do the 1.1 assignment. It's more of a qualitative assignment. We haven't calculated anything yet, except I think I might have some questions on there and figuring out frequency and period. I didn't do any of those, but you can take a look at the answer key if you run into a snag. All right, we'll see you again.